In this brief talk, we concisely overview our recent ICLR paper on efficient generalized spherical CNNs, which you can find on the archive for further details. Data on the sphere arise in many applications, from Earth and climate science to medical imaging and molecular chemistry and beyond. Whenever observations are made over angles, we recover data on the sphere. For example, the cosmic microwave background, the relic radiation from the Big Bang, is observed on the celestial sphere, while 360-degree photos and videos in virtual reality are also observed on the sphere. To transfer the remarkable success of deep learning to applications involving spherical data, we need deep learning models such as CNNs defined natively on the sphere. Just as planar CNNs encode translational equivariance, one of the key factors responsible for their success, spherical CNNs should encode rotational equivariance. The construction of spherical CNNs has received considerable attention in the recent literature. In this work, we develop a generalized spherical CNN framework, which comprises three components, including convolution and nonlinear activation operators defined inherently on the sphere. The framework builds on numerous influential spherical CNN constructions by Cohen, Estevez, Condor, and collaborators, and supports hybrid models that allows different types of spherical CNN layers to be leveraged alongside each other. Existing spherical CNN layers are highly computationally demanding, in many cases prohibitively slow. In this work, we develop new computationally efficient spherical layers to be used as the primary building blocks in this framework. We introduce four key developments to yield efficient generalized spherical CNNs. We introduce a channel-wise structure and apply strictly rotationally equivariant tensor product activations to each channel separately, which reduces the computational complexity associated with representational capacity from quadratic to linear. Under this new multi-channel structure, we decompose the generalized spherical convolutions into three separate constrained convolutions. Firstly, with a uniform convolution to project down to the desired shape, followed by channel-wise and cross-channel convolutions that can be seen as analogous to depth-wise separable convolutions often used in planar CNNs. These constrained convolutions significantly improve computational and parameter efficiency. We introduced optimized degree mixing sets of the tensor product activations to mix information between degrees in a reduced set of connections. To construct these optimized mixing sets, we consider subsets of the full mixing set. We consider a graph representation of the mixing set with edges weighted by computational cost and recover a minimum spanning tree with further logarithmic subsampling. This reduces computational complexity significantly. Finally, we also adopt efficient sampling theory on the sphere and rotation group to avoid discretization artifacts and leverage fast algorithms for harmonic transforms and convolutions. We perform a number of numerical experiments to evaluate the properties of our framework and to evaluate its performance on a number of common spherical benchmark problems. The efficient spherical layers developed provide orders of magnitude savings, both in terms of computational and memory cost, as shown here as a function of increasing resolution or bandlimit of spherical images. The tensor product activations are computed purely in harmonic space and so are strictly equivariant, with mean relative equivariance errors at the level of floating point precision. We applied our framework to the problem of shape classification and retrieval, for which rotational invariance is critical, where 3D meshes are represented by various projections onto different spherical channels. Our approach performs very well, achieving state-of-the-art performance in 4 of 6 metrics, and notably needs many fewer parameters than alternative approaches. We also consider the problem of predicting the atomization energy of molecules. On this problem, our framework performs exceptionally well, again achieving the state-of-the-art not only in terms of RMS error, but also in terms of parameter efficiency. To summarize, we have introduced an efficient generalized spherical CNN framework that builds on the layers of existing approaches to allow them to be leveraged alongside each other, while also introducing a number of new efficient layers to be used as the primary building blocks of the framework. We achieve state-of-the-art performance, both in terms of accuracy and parameter efficiency. We're very open to collaboration, and please don't hesitate to get in touch if you'd like to discuss further. Thank you.